Our talk tonight is the life cycle of dust in galaxies. We have an astronomer in the Office of Public Outreach who studies dust, and I got to say that some of the other astronomers, give them a little bit of a hard time, like, oh, you're looking at dust out there. A can of pledge could wipe you out. Well, this is actually one of the most important things in astronomy, and Margaret will be able to show you the splendors of dust in the universe tonight. Upcoming next month, Tom Brown, who was gracious and postponed his talk when we had a special guest speaker a few months ago, will talk about On the Trail of the Missing Galaxies, the oldest stars in the neighborhood, in our local galactic neighborhood. October, Bill Blair from across the street, Johns Hopkins, will present a multi-wavelength view of stellar life and death in Messier 83. Or another talk. Actually, he had another title. He had like 4 different titles he was suggesting. This is the one that I said, oh, this sounds good, Bill, but he hasn't gotten back to me as to which one he'll actually choose. But it'll be about supernovae in the galaxy Messier 83. In November, unfortunately, our speaker TBA is back, and he keeps popping up every now and then. This, I will note, is on November 1st. It's not on election night. Election night will be November 8th. So the week before election night, maybe we can have a debate, No, absolutely not. We don't do politics here. But please come the week before you vote to our public lecture series. I'll have that speaker for you in a bit. The construction, as you know, San Martin Drive south of STSCI will be closed until approximately September 2016. So to get here tonight, you had to approach STSCI from the north. However, you'll notice that's September 2016, so by the next month, things might have changed. If you go to this website, it says that Phase 1 is scheduled to be completed at the end of August, with Phase 2 to begin immediately afterward. That means that next time we have this, it could be, see all this blue stuff here that's currently closed? It could be then the red stuff and the yellow stuff will be closed. So instead of coming from University Parkway south to STSCI, you will have to come from Wyman Park Drive to come north to us, okay? So approach us from the south. So next month, I expect I will have this one that between September and December, the north part will be closed, so approach from Wyman Park Drive. If you are on our email list, I will, the day of the lecture or before the lecture, make sure that you get the proper instructions as to whether come from the north or from the south, okay? Or you can just check this website for yourself. Our website, where you'll get information like this, is, well, if you just search Hubble Public Talks, you'll find it in your favorite search engine. At Hubble site, we have a Go link, hubblesite.org, Go Talks. You get the list of the upcoming lectures. You have links to the live YouTube and STSI webcasting feeds, as well as the past lectures on YouTube and the STSI webcasting, and the easiest way to sign up for our email list. You can subscribe or even unsubscribe here, all right? Our email announcements, if you don't want to use our webpage, can be found at maillist.stsci.edu. It's called Public Lecture Announce. Last thing, if you have questions or comments, social media, we are on Facebook. We have 2 Twitter accounts. We're on Google+. We have Pinterest. I'm also on Facebook, Google+, and Twitter occasionally. And I have a blog on Hubble's site. All right. The observatory, the weather appears to be permitting. So it looks like there will be observing tonight. This is the Maryland Space Grant Observatory, which is on top of the Physics and Astronomy building across the street here in Hopkins. So you can go up and do a little bit observing afterwards. Duncan will probably be here at the end. If I forget, somebody remind me, hey, what about the observing? Because you'll just sort of meet. If you cannot go over by yourself, you got to go over with Duncan, because you got to go through get into the building and through some stairs and up, and you have to go as a group, okay? All right. News from the universe for August 2016, and I will apologize, it's going to be a little abbreviated because we've been really busy in the Office of Public Outreach lately. I didn't have enough time to prepare full stories, but I do have 2 short stories for you tonight. Our first story, the final frontier of the universe. If you keep up with popular culture, you know that this year is the 50th anniversary of Star Trek. The Star Trek series 50 years ago. How many seasons did the original Star Trek TV show last?
3.
Just 3. It's amazing that this franchise has lasted so long, but the original TV series was only 3 seasons. Well, we here at Hubble and NASA like to get in on a good pop culture reference. So, well, we don't have spaceships that can explore the universe. We don't have warp drive to boost us to the far side of the galaxy. But we do explore the universe, and we use a version of nature's own warp drive. What we do have is gravitational lensing. The mass of giant clusters of galaxies actually warps the fabric of space around them. And using that spatial warp, the light that passes through it is redirected such that the light actually acts like a lens and focuses and amplifies the light that passes through it. So we have gravitational lensing that we can use to look at the most distant reaches of the universe. And we have done so in a project called the Frontier Fields. And for the press release that we did celebrating in honor of the new Star Trek movie and Star Trek's 50th anniversary, we released the final of our Frontier Fields, Abell S1063. So what you are seeing here is this giant cluster of galaxies, all these galaxies here that are so massive combined that they warp the space around it. And then the galaxies that are behind it, the light that passes through gets warped, it becomes distorted. You can see these long, streaky arc things. Those are gravitationally lensed arcs. They are the images of galaxies behind the cluster that have become stretched out as the light passes through that cluster of galaxies. All right? It also amplifies the light, makes it brighter, so that we can see fainter galaxies by looking through this cluster than we otherwise could. All right? The Frontier Fields project is one of the largest projects ever to get time on Hubble. And it not only observes these giant clusters, but while one instrument is observing these giant clusters, another instrument is observing a random field relatively nearby. And so we also have these deep fields that we can release because we process 2 images at the same time. One of the cluster, one of this parallel field. And these parallel fields are very deep images of the night skies, like the Hubble Deep Field and Hubble Ultra Deep Field. So using the nature's warp drive, we are exploring the frontiers of the universe with the Frontier Fields project. And if you think that sort of play on words was bad, you ought to read the press releases because they get really bad in terms of trying to use the play on words. But it was a way of connecting with the Star Trek 50th anniversary and showing off the deep, deep images we are getting of the universe with the Frontier Fields project. Our second story tonight is about the heart of the Crab Nebula. Now, in 2000 or 2001, we released this image of the Crab Nebula. The Crab Nebula is a supernova remnant. This is a star that was observed by Chinese astronomers to have exploded, from our point of view, 1,000 years ago. We saw the star brighten 1,000 years ago. It was bright enough to be observed in the daytime for about a month. Okay, and when we look in that same spot in the sky these days, this is what we see. We see the guts of the star just blown out across space. And so this is Hubble's image from, this is a WIFPIC 2 image of the Crab Nebula. And you can see all of the material of the star that blows out into space. Now, at the center of the Crab Nebula, the beating heart of the Crab Nebula, is something called a pulsar. And so we just released in this month this image of the core of the Crab Nebula. All right, and you can see that filamentary structure, but you can also see these rings around here circling around at the center, which is where the pulsar is. Now, a pulsar is a neutron star that is spinning. Okay, and a neutron star is basically an atomic nucleus, all right, that weighs as much as the sun. right? Because all of the material at the end of this supernova explosion collapses, the core of it collapses to become this really super dense neutron star at the core. And it is spinning so fast that the heart of the Crab Nebula spins 30 times every second. This was a signal that was discovered by radio astronomers in the 1960s, and I believe this was originally called LGM-1, as in Little Green Men #1, because we didn't know what it was back in the 60s. We now know that it is a neutron star spinning 30 times a second, and it has an intense magnetic field. And here you can actually see the rings around here are material that is actually moving away, and you can see the material. And we actually have time lapse of this where we can actually watch the material move away from the Crab Nebula. One of the few things in astronomy that changes during our lifetime. There was no new science result released with this image. This was just a reprocessing of other data that we had gotten, but going in deeper and seeing the heart of the Crab Nebula. Okay, that was our Hubble Heritage release for July. Question?
Yeah, why isn't the neutron star in the center of the mass of the supernova?
Well, if I go back to this image, the neutron star is about in here. Okay, the two images are actually at slightly different orientation. Okay, I think the image is rotated about 110 degrees from this image. I was going to align them up, but I didn't quite have time today to do that. Sorry about it. All right, but yeah, it is in the core of that nebula. By the way, this nebula here is about 10 light years across. Okay, so it's gone from being a single star to being about 10 light years across over the course of 1,000 years. All right. Okay, so now we go to our featured speaker. And our featured speaker tonight is Margaret Meixner. She and I first met at the University of California, Berkeley, where we were doing our graduate school together back at Berkeley. There are actually several from our group of astronomers grad students going through Berkeley that are working here at Space Telescope. So obviously we were just an amazing group of grad students, right? Several of us ended up here. Margaret, however, was the most exceptional of all of us, as evidenced by after she graduated and got her PhD, she didn't go do a postdoc. She was offered an assistant professorship at the University of Illinois. She went straight from grad school to being a professor. That just almost never happens, okay? That tells you how special she is. Fortunately, University of Illinois couldn't keep her, all right? And in 2002, she came here to the Hubble Space Telescope Science Institute and has been here for, I guess, 14 years now. That makes it. Yeah. She is an expert in dust, of course, but she's also really, really good at doing very large observations, very large survey observations. The last talk you gave here was on planetary nebula, right? But you've done since then done a number of very large surveys, and she's done them so well that they've actually put her in charge of a lot of things. And her current position as deputy of the instruments division here, I think she's pleased to be able to talk about the science work that she loves so much. So, ladies and gentlemen, Dr. Margaret Meixner.
Let's see. Can you hear me? If you can in the back, wave your hand. All right, good. All right, so I'm going to talk to you about the life cycle of dust in galaxies. And the subtitle here is from these large surveys that Frank was telling you that I love to do, insights from Spitzer and Herschel. Spitzer and Herschel are two infrared space observatories that flew. Spitzer's still out there. And I used it to survey the Magellanic Clouds. How many people have heard of the Magellanic Clouds before? Oh, wow. Very, very well-educated audience then. All right. So this is a picture of the large Magellanic Cloud that's a combination of both Spitzer and Herschel data. And it looks very disky. It has all this frothy, very colorful things. And I look at it and it's like, wow, this is beautiful. I mean, isn't that beautiful? And I look at it and say, this is beautiful, but I can't help but thinking about all the dust that's in it that's causing it, because all this emission you see here is actually from the dust in these galaxies. And in particular, I ask myself the question of, why does this galaxy have dust? Because as you may have heard in these forums, the whole universe began as mostly hydrogen and helium and maybe a few other elements, but we've got dust now. So how did it get there? So what I'm going to be talking to you about is the life cycle of dust in galaxies, and I'm going to use this cartoon to describe how dust gets there, or the processes in there, and also how little we know about it. So let me go through this, because I'm going to use this as a narrative tool throughout the whole talk. So at the center here, we have what I call the origin of dust. So dust can be formed in the atmospheres of AGB stars. So AGB stands for asymptotic giant branch stars. These are dying stars, like our sun will become an AGB star, and they blow winds and send out dust. Dust may also arise in supernovae. So Frank just talked to you about the Crab Nebula. The Crab has dust in it. And that's a type 2 supernova. That's when a massive star explodes. Type 1a supernovas are being looked at, but that's more like a white dwarf pair exploding. So anyway, these are where the new grains come from. And they get injected out and drift out into the interstellar medium. And they're in the interstellar medium, they get processed a lot. So these same supernovae that create dust will also send huge shock waves in the interstellar medium, and they'll shatter the grains. And then these grains will drift around, because the ISM drifts around, into the intercloud medium. Clouds will form out of these, and the dust kind of gets dragged along with the gas in there. And then they become cold clouds, and maybe in the cold clouds you get growth of dust. That is, the grains grow bigger because they're cold and they get mantles around them, and maybe they just start sticking and grow. And then this whole cycle out here, the ISM can happen around, but also from these dense clouds you can form young stars. And so young stars form. And then they grow up to main sequence stars, and then the whole process starts over again. So that's why we call it a life cycle, because stars have a life cycle. And because stars have a life cycle, and they are in some sense the sources and sinks of dust, dust has a life cycle. All right, so let me talk a little bit about the Magellanic Clouds and why I chose them for this study. First of all, they're nearby, so proximity is helpful. The Large Magellanic Clouds, about 50 kiloparsecs away. The Small Magellanic Clouds is about 60. And you multiply that by kind of 3.3 to get light years. But if you ever go to the southern hemisphere, you can see the Magellanic Clouds with your own eye at night. It's quite a sight. They're beautiful visions to see. The Large Magellanic Cloud, which I'm going to be, because I'm affiliated with NASA, I love acronyms, so I'm going to call it LMC for Large Magellanic Clouds. It's kind of nearly face-on. Remember that first picture I showed you was kind of disc-like? So it's nearly face-on. And the combination of both these things, the fact that they're kind of close by, and the LMC in particular is kind of face-on, you can separate the stars from the interstellar clouds, and then watch and monitor their interaction between each other, because you can separate them. And because it's nearly face-on, you can kind of look at a dust cloud and say, well, I think it's really associated with this gas cloud and stuff. So there's a lot of clarity and information you can get from these systems. Now, the Magellanic Clouds have been interested for a lot of reasons throughout the history of astronomy. They're sort of a stepping stone between galactic and extragalactic studies. Their mean metallicity, which means how many metals is anything heavier than helium, really, is the LMC is about half solar, so it's less half of the metallicity of our own sun in our own solar system. And the Small Magellanic Cloud is 0.2 times that, so sort of 1/5. So it's less. And this metallicity is interesting because the ISM, or the interstellar medium in the universe, and in galaxies in the universe, had a peak star formation epoch at a Z about 1.5. But the mean metallicity of the Magellanic Clouds is actually brackets what happens during the peak star formation epoch. So if you study sort of the astrophysical processes in the Magellanic Clouds, you might get some insight of what was happening during this major event in our universe of star formation. And then the dust content, that is what we call the dust to gas ratio, is lower than our own galaxy. Again, about half of the Milky Way's dust content, and for the SMC, it's about a tenth. And then some other interesting aspects. So the large and small Magellanic Cloud have known tidal interactions between each other. They're a pair. And possibly the Milky Way. And they've had a very long history of studies, of all sorts of studies. They've been a proving ground for lots of studies. I mean, for example, the whole famous Cepheid's relation, which people use for distance indicators, that was first established in the Magellanic Clouds. And so for a number of reasons, this is sort of an ideal case study for galaxy evolution. All right, so what I did is I led 2 large surveys. And the work I'm showing is actually from a team of sort of over 100 scientists worldwide. But I helped organize the effort. With Spitzer, we called it surveying the agents of galaxy evolution. The agents are the stars in the interstellar medium that really create the environment. And we also called it the Herschel inventory of the agents of galaxy evolution. So we called them SAGE and Heritage. And what we have here are what we call spectral energy distributions. So this is sort of the energy or flux coming out of the galaxy on the y-axis, and on the x-axis we have the wavelength in microns, because infrared astronomers like myself like to think about microns. This is 10, 100, 1,000, and then kind of shaded in here is the range over which the Spitzer Space Observatory covered. So it goes all the way from there to there, and then Herschel covers from here to there. And so together you actually get the whole thing. Yeah, you get a little bit of the stars, but the whole thing about the dust. You get the warm dust with Spitzer. With Herschel, you get the colder dust. You get the whole complete picture with it. And what I'm going to talk to you about is the complete picture that we're learning from these observations. So this image here, I like this image because it kind of shows that whole dust life cycle with the 3 colors. So this is from Spitzer SAGE of the Large Magellanic Cloud. And in purple here, this is from the Spitzer IRAC camera at 3.6 microns. And you can see all this blue here. You can see kind of a faint glow of a bar. And if you look in the optical, the bar is very prominent. But here, it's a little fainter compared to the other dust things. But here, what we're tracing here is what I call the old stellar population, the old and dying stars. And these are the stars, remember, that are producing the origin of dust. So this blue glow here is sort of where lots of dust is originating from. And then in green is sort of a tracer of the dust in the interstellar medium itself. So that's the ISM processing, growth, destruction. That's the IRAC 8 micron emission. And then in bright red here, this is this MEPS 24 micron camera that picks up sort of hot spots where massive stars are being formed in this galaxy. And so this one image kind of shows this whole life cycle. Now, just to show you a complement, I'm going to be showing pictures of the SMC and the LMC. This is the small Magellanic Cloud. This is the Herschel Heritage image. And in Herschel, remember, all we're seeing is sort of dust emission from the interstellar medium. That second bump is all interstellar medium dust. And you can see some brighter spots sort of where the dust is warmer, redder spots where it's cooler. All right, so let's go back to our problem at hand about why do galaxies have dust. So this is, first of all, we asked the question, how much dust are we talking about? I mean, how much do we actually need to keep there for galaxies to have dust? Well, in the LMC, it's 7.3 times plus or minus 1 times 10 to the 5 solar masses of dust over the whole galaxy. So that's how much dust is in this galaxy, and this life cycle in some sense has to maintain or balance to keep it And in the small Magellanic Cloud, it's less. Everything is smaller in the small Magellanic Cloud. It's 8.3 plus or minus 1 times 10 to the 4. So it's about a factor of 10. And everything about the small Magellanic Cloud is about a factor of 10 smaller than the large Magellanic Cloud. All right, so let's go back to this life cycle of dust. And I want to show you what we've learned from these surveys over the past, gosh, almost 10 years. I started this about 10 years ago. And first, we're going to start off with the origin of dust. So where does dust come from? What have we learned from these surveys to tell us about how dust is produced in polluting the galaxies? So first, I'm going to talk about asymptotic giant branch stars, AGB stars. And this is my favorite picture of an AGB star. It's actually from one of the hottest new observatories, the ALMA observatory, the radio observatory in the southern hemisphere in Chile. And it just shows, it looks kind of circular, but there's also a spiral pattern. And it's just puffing out the dust along with molecular gas in this star. In addition to the AGB stars, a more massive star, things that go boom and explode, is a red supergiant. And this is a Hubble image of VY Canis Majoris, showing sort of the heart of it in a reflected, and all this light here is basically starlight reflected in the dust, by the dust surrounding this star. All right, so in the large LMC and small Magellanic Cloud, we had to identify which of the stars are actually dust producers. And we do that using these diagrams called color magnitude diagrams. And so what this is we measure the flux every star in the galaxy, and then we plot that flux. We use this system, astronomer system called magnitudes. And so this is 8 micron emission in magnitudes. And this is the color. So this is J-band, so this is about 1 micron minus 8 microns. And so as you go to the right, you're getting to a redder and redder star. And as you go up, you're getting to a brighter and brighter star. And the pattern of this contour is sort of the location, sort of a density plot of all the stars in these respective galaxies. And what we've identified here, there are all sorts of features. There's structure in this contour plot. And that structure is actually different types of objects. Red supergiants and the AGB stars are there, but there's a lot of other things. And so the first job is to find out and identify those sources that are the AGB stars and the red supergiants. And then you have to sort of model how much dust is around them. And for that, because we have all the measurements for the dust, is we can, again, create a spectral energy distribution for every star in the galaxy, every AGB star. Again, this is how much flux or energy that's coming out versus wavelength. There's 1 to 10 microns. And this is a case of an oxygen-rich source. And how do we know it's oxygen-rich? We look at its spectrum. And I call this thing grams, because to calculate all the dust in all these stars, there were a lot of stars. There were like tens of thousands of them. So we created a grid of red supergiant and asymptotic giant branch models. We called them grams because we were weighing the dust. And we used this particular source to figure out the type of dust. And so this spectrum, there's a little feature here and there. And this is indicative of silicates in the star. So you can take a spectrum of silicates in our own galaxy. You would see the same. It's in our own laboratories, and you see these features. And so we know it's silicates from the spectrum. And then we model the energy in silicates here. And from that modeling, we can determine the luminosity of the star and what we call the dust mass loss rate. And so this is the luminosity. So it's 5,088 times the luminosity of our sun. It's much, much more luminous than our sun. And our sun will get this luminous when it dies. And then this is the amount of dust it's producing per year, this one star, 2 times 10 to the minus 9 per year. All right, so that was for an oxygen-rich star. Where does carbon dust come from? Things like polycyclic aromatic hydrocarbons and carbonaceous dust and soot. That comes from things called carbon stars. And a carbon star again, is an asymptotic giant branch star in which the innards of the star has churned out enough to change the chemistry on the surface of the star from oxygen-rich, which is pretty much what the universe is, to something carbonaceous. And we know that these stars have carbonaceous dust because they're mostly featureless, except there's a little feature here from a silicon carbide feature, SiC. And so again, we used grams and we modeled what is coming from this star with the spectral energy distribution. And we find out that it's also over 5,000 solar luminosities, and it's about 2.6 times 10 to the minus 9 solar masses of dust per year. All right, so those are two example stars and the types of dust that we get from them. But again, we have like thousands, tens of thousands, 30,000s of these stars. And so what we did was we created this grid, and this is a representation of the grid on a color magnitude diagram of the 8 versus 3.6 minus 8. And in gray are all the models we created. And then in blue are all the sources in the Large Magellanic Cloud. So blue is where all the LMC oxygen-rich sources are. And in red are the carbon-rich sources, because there's two types of dust, carbonaceous and silicate-based dust. And they all go out. All right, so what are other things that we've learned about these stars? Well, I mentioned the oxygen-rich sources, the carbon-rich sources, and then this shows, in some sense, the luminosity function. I was telling you that we have sources that are 5,000 solar luminosities. We have some that are even greater than that. So in the blue here is the oxygen-rich sources in the solid line. The SMC, it's been scaled up, but that's for the SMC. And again, for the LMC, we have the red solid line for the carbon sources and the dashed line for the SMC. And then what I've shown here is sort of it's a dashed line of the separating what we call the AGB, or the asymptotic giant branch stars, from the red supergiants. And this is important because these types of stars on the right are the stars that explode as supernovae. Those are the massive stars that explode, whereas those on the left are the ones that are going to die quietly, like white dwarfs and planetary nebula. And one point I want to make here is that you can see that the carbonaceous winds only come from the AGB stars. Red supergiants don't churn up carbon. So a lot of people think a lot of the carbonaceous dust in the universe comes from stars like our sun when they die. All right, so we've applied these Graham's models to all the populations in the Large Magellanic Cloud and Small Magellanic Cloud, and said, okay, well, how much dust are we producing? So this is what, on the y-axis, we call cumulative dust production rate in solar masses per year. So this is 10 to the minus 5 solar masses, 10 to the minus 6. And what I show here in the black are all the sources in the LMC. Red is, again, carbon sources. Blue is oxygen-rich sources. And again, you can see the SMC is smaller than the LMC by a factor of 10. Just to show you what some of the numbers are concretely, so there have been a couple of papers by former students of mine, one by Riebel, where he says the total dust produced in the LMC now by these stars, these stellar winds, is 2.1 times 10 to the minus 5 solar masses per year. It's quite a lot. In the SMC, it's about 8.9 times 10 to the minus 7 solar masses per year. And then what is the breakdown? So in the LMC, it seems to be dominated by carbon-rich dust production. So we have more carbon-rich dust being produced by these stars than the oxygen-rich dust. And in the SMC, it seems to be more 50-50. And then when you look at the oxygen-rich dust, remember you can have sort of the lower mass stars like the AGB stars and the red supergiants. So the red supergiants, it's only about 9% in the LMC. And the SMC, it seems to be about half and half, 25% red supergiant, 25% AGB. So you kind of look at the red supergiants and you're thinking, well, the massive stars really aren't doing very much. It seems to be all the kind of lower mass, solar mass stars doing most of the work. And, okay, this is okay. But the truth is, maybe things happen later in the massive star's life. And it turns out that as the massive star gets closer to death, it has more phases than the lower mass stars. So this, for example, is what's called a luminous blue variable, and this is the iconic one from the Hubble image of Eta Carinae. This is not in the LMC, but there are objects like that in the LMC. And this is one of the more famous luminous blue variable objects, R71. It has a dust mass of 8 times 10 to the minus 7 solar masses per year. And there are 5 LBVs in the SMC, and it's possible that if all of them, each of them, have that much dust production, you actually get a pretty hefty amount of dust coming from these LBVs, 4 times 10 to the minus 6 solar masses per year. But, you know, it turns out that, let's see if I can get this to go. Oh, there we go. There we go. Turns out that the massive stars really do produce a lot of dust. And when it happens, though, is at the very, very end of its life, when it explodes. So Frank's talk about the heart of the Crab Nebula, this is sort of a movie version of how the Crab Nebula was created. It's basically a star exploding and dying. And one of the largest surprises for us in the Magellanic Cloud search was that we actually detected dust in 87A. It was pretty much a discovery, I mean, and that people are rapidly following up on. So this is supernova 1987A. This is a Hubble image of it. It's still monitored by Hubble, and Hubble launched shortly after this thing exploded. And this is a picture of the field in Hubble, and this is a picture of our Herschel Heritage image. And we found it, and I remember the phone conversation when we were trying to pick follow-up sources of supernova remnants to follow up on with the spectroscopy capability of Herschel. And a postdoc was going through, and she says, oh, we have N49. I was like, yeah, okay. N132 is like, okay, that's exciting. And we have 87A. I said, well, hold it there. We don't have 87A. We're not supposed to see it. She says, well, I'm sorry, but we see it. And I was like, okay, well, that's very, very interesting. And the interesting thing about it is here we have a close-up of 87A. Here's the ring. This ring was created by the prior, remember I was talking about the stellar winds and the red supergiants creating those winds, that material drifts out. That's what the ring is. It's that prior progenitor star wind. And at the heart of it is the ejecta. So this is the exploded star, and this is the star from the prior wind. And here it is in X-rays as well. And when we were proposing to observe the LMC with Herschel, we said, well, can we see 87A? Because it's such a famous object. If we can see it, we should tell them we're going to see it. And at the time, this is what we knew. Okay, well, here is, here's what we got with Spitzer, and Spitzer went up, and then up, Spitzer came down. And so we said, well, you follow this line down. Again, this is one of these spectral energy distribution where you have the amount of energy and the wavelength, and you keep going down, and well, here's where Herschel started, and we were on this yellow line, and we're like, there is no way we're going to detect this object. And so when we detected it, we're like, wow, what is this? And so what it is you can see sort of 2 peaks of dust, the ring dust. We said, this has got to be in the ejecta. We said, the ejecta? Really? Well, how much dust would you need to create this much emission in the far infrared? And it turns out it's about 0.4 to 0.7 solar masses of dust. And there's a large uncertainty because we don't know the composition of this dust yet. That's actually something I hope to tackle with James Webb. That's a lot of dust. I mean, no one has ever seen that much dust in a supernova remnant before. Most of the dust people see is like 10 to the minus 3 solar masses of dust from prior measurements. So this was really, really quite remarkable. And we published it in Science, and people got all excited, but they kind of said, look, you got some kind of fluff there. You really, you don't have the resolution. I don't think it's a supernova. You're like, okay, we're going to go look at it with this hot new telescope called AMA, and we're going to measure from the ring emission to dust and see if it's there. We think it's going to be there. So they got the time, and this is what it looked like going at from these longer wavelengths. So this is really testing finding the ring emission, but there's a lot of synchrotron emission. And then as you go to the shorter wavelengths, you get more into the dust emission. You can see, well, there's a ring, and hold it, there's something in the center, and when you go to the highest line, it's in the center. And so this very clearly, it silenced all the critics who said, oh yeah, gosh, you do have a lot of dust there. And all the theorists are running madly around trying to figure out why. All right, so that's the story of dust production. So let's talk a little bit about what happens when these dust grains go out into the interstellar medium. All right, so here's a supernova remnant in the Large Magellanic Cloud, N49. This is a beautiful composite HST, glorious detail with Chandra in the blue because it's a hot plasma. And so because of the 87A discovery, there's a student at Kiel, and she said, well, I'm going to look around at all the supernova remnants and see if they have dust in them. And so she looked, and here's N49. And these plots, these color plots I'm showing you here, is her study showing on the left here, this is dust mass. And on the right, this is dust temperature. So it's like a little map around N49, which is in the circle here. And on the top is cold, sort of cold dust. This is warm dust. That is two components she modeled. And so here at the center, you can see that, well, on cold dust, doesn't really seem to be much there. There seems to be some warm dust, some mass and warm dust. And here again, this is cold and this is warm. But really, when she looked at the whole sample, she really did not find much dust at the center of these things. And some of that could be a limit to the sensitivity for Herschel. And mostly what she measured then was what happened to the surrounding parts. And she found that really, well, gosh, these supernova remnants, as they go out, they're really destroying the dust. And so her paper showed that there's some dust destruction. And then we did a slightly more rigorous calculation on the supernova remnants in the Large Magellanic Cloud. And here's all of them in the red circles. And this is sort of the amount of dust that's destroyed by them. So this is the number of supernova remnants. And this is how effectively they are destroying the carbonaceous dust in the interstellar medium or the silicate dust in the interstellar medium. You can see that the silicate dust is actually more readily destroyed than the carbonaceous dust. In fact, you can kind of figure out what is the average lifetime for dust grains. So these stars produce the dust, and they kind of hover out in the interstellar medium. How long can they possibly last, given all these supernova remnants sweeping through? So this is dust lifetime. This is a parameter, sort of how thick is the LMC along the line of sight. This is the LMC and the SMC. So to get a dust lifetime, you say, well, how much is the total mass of dust? And that was the number I gave you at the beginning of this talk. How much is the total mass in the galaxy of dust? And then what is the average amount of dust destroyed per supernova remnant? And that comes from a theoretical calculation. And then this is the rate of supernovae, which is just sort of the rate at which stars are formed that are massive enough that can explode. And what you get in the LMC is that, well, silicate dust grains can only live 26 to 42 million years. Really, really short. I mean, remember, how old is our sun? Anyone know that? Billions? 5 billion, right. And it's going to get up to 10 billion before it dies. So here's 42 million. So a lot shorter than the lifetime of one of our stars. So dust is destroyed in the interstellar medium. And the question is, do we have any evidence that it grows back? And here we've been looking at maps of dust to gas ratio. So we're using the Herschel images, and we're figuring out, we get a total map of the dust. I showed you that at the beginning. And my colleague Julie Roman Deval said, okay, well, I'm going to compare it to the gas and look at how the gas to dust ratio fits in. And here in the SMC in particular, you can see that here's a gas cloud that's showed here in the contours. And you can see that the gas to dust ratio appears to be lowest. That is, the amount of gas per dust is lower when you get to these gas clouds. So just to flip that around, that means there's more dust, apparently more dust in these clouds than gas in these denser clouds. So the tricky thing is, though, that it's a hard thing to prove with these measurements because they're kind of coarse. The measurements are, they're factors of 2 or 3 uncertainty because we're using all these model fits and stuff. And so we said, well, okay, let's use a more precise tool. Let's use spectroscopy. And so another way of studying where dust is what we call metal depletion on the dust grain. So what is dust made of? So we kind of think of the dust bunnies under our carpet, but actually if you analyze those, maybe it would be similar, but it's basically anything that has metals. So it could be iron, it could be carbon, it could be oxygen, silicon, all bound together in these complex solid features. So it's made of metals. These have things much heavier than helium. And if you look along the line of sight towards a star, you can look in reflection and you can see how many metals are there. And you can compare it to what we know should be there. And then a depletion is basically the metals that are missing from the interstellar medium. All right, so let me just walk you through this a bit more. So here's one of the stars we looked at. Here's a spectrum from an ultraviolet spectrum. So these are measurements taken with Hubble and with Fuse. And it shows, again, here's wavelengths, and here's fluxes. And you can see these dips here. This is absorption dips from gas in the interstellar medium. And it's absorption dips due to iron, or silicon, or zinc, or magnesium, or chromium. And all of these are trace heavy metals that we use to understand and trace where dust is forming. So we measured these for a number of different species. So this is iron, and silicon, and zinc, and chromium, and phosphorus. This is in the SMC. And we plot basically how much stuff is missing compared to sort of a rolled up number on that, rolled up depletion. So this is more depletion, that is, you have more of the metals in dust, and then less depletion, less metals in dust. And this black line here is what happens in the Milky Way. So this is comparing the Small Magellan Cloud to the Milky Way. And by summing up all these metals that are missing, you can estimate gas to dust ratios from basically what's missing in a much more precise way than we can with the maps. And so it's a good check. And so what we have here is the hydrogen to dust mass ratio, the gas to dust ratio for the SMC, the LMC, and the Milky Way. And we can see that it changes. You have lines of sights that things are more depleted, that is, there's much more dust, and you have regions that are less depleted. And so this is other confirmation that there are actually real variations of how much dust is contained in different parts of the galaxy. There's real processing out there. It's both destroyed by the supernova remnants, as I showed, but then also in the colder clouds, it really seems that it is growing again. Now, this is sort of evidence that exists, an existence proof, but we are not as far along in terms of coming up with a rate. Like I showed you nice dust production rates by the evolved stars. But all we've done so far, but I think it's a big step forward, is to show that, yeah, actually this stuff happens. We don't know how fast it happens, how effective it is, but it's certainly happening. All right, so let me go on to the last loop here, the young stars forming the stars. Now, in terms of the life cycle of dust, how this is important is that the dust grains actually disappear, because when you form a star, it kind of takes all the gas, all the dust, and it makes them all atoms, in fact, like highly ionized atoms, when it forms the star. This is, again, a beautiful Hubble image of a beautiful forming or young stellar object, because that's what we found in the Magellanic Clouds, young stellar object, S106, showing these beautiful bipolar nebulas. And YSOs, or young stellar objects, have different kinds of evolutionary stages that we learn about and can pick up with these observatories. Here's a young protostar, main accreting phase, stage 0. It's basically just a bunch of cloud condensing onto things. It's very cold. It's really only seen with Herschel. So we were good at finding these types of objects, and then we have stage 1 objects. This is sort of an accreting protostar where you have a disk, it's turned on, you have infrared excesses, and then stage 2 is when basically that envelope's gone, but you still have this disk and planets will start forming. And stage 3, which I won't be talking about at all, really 2 or 3. Stage 3 is where basically you have planets and you're seeing sort of Kuiper belt type objects. All right, so small Magellanic Cloud, YSO candidates. So again, how do we find these? So I talked to you a little bit, this is maybe somewhat familiar. We use these color magnitude diagrams again. This is 8 versus 8 minus 24. And the thing with the YSOs is that before the launch of Spitzer, there was only one known in the small Magellanic Cloud. And in the large Magellanic Cloud, there were only 20. So to really understand this, we actually had to find all the young stellar objects. So this was a big discovery, just trying to find them and identify them for the first time. So it was pretty exciting. It was a lot of cool stuff. What I want to show over here is these are all the evolved stars. So these are all the ones I talked about at the beginning of the talk, the ones that are dying. There's confusion with the ones that are being born because they both have stars with dust around it. And here's the young ones. These are the ones we were after, and there were some studies done before to show some of them. And then this is what this was our guidance. So in gray here and all the things, it's basically the whole catalog for the small Magellanic Cloud, the whole catalog of all the sources. And in amber here is the model predictions of where do you expect to find them in the color magnitude space. And then here, well, this is a problem. The problem here is that there are a lot of background galaxies to the LMC that confuse us with whether it's a star or a galaxy. So the initial surveys, the one published by this former postdoc of mine, Marta Sevilla, basically went for the easy stuff, the really dusty stuff and the bright stuff, so kind of the more massive young stellar objects. And so what we did is we found actually 1,100 YSO candidates in the SMC. So that's 1,000 times more than we knew before the survey was done. 1,000 times more objects. And this is the location of all of them. So what are some of the things that are interesting, particularly with respect to this dust life cycle? Is, well, you can start making plots, histogram of the stellar mass here. You can see we're kind of biased to the more massive ones. Here's the luminosity plot, again, the more luminous ones. But there have been lots of theoretical studies shown of figuring out what an initial mass function is. And this is a characteristic initial mass function that we just fit to the part that we're most confident with. And we figure out how many stars are being born now. And from that, we can come up with a star formation rate, or SFR. And that star formation rate in the SMC is 0.06 solar masses per year. And so that's the rate at which stars are forming. If you have a gas to dust ratio, you can also say, well, how much dust is disappearing because I'm forming these stars? All right, going to the less evolved, the young stellar object and dust clumps, we got those from the Herschel Heritage Survey. So this is H alpha, Spire 250 microns, and this is our band merged catalog. And then bottom here, you can see where we think all the YSOs are located. And then we also found kind of pre-forming stars, sort of dense clump things. And then you can see we have lots of contamination from the background galaxies at these wavelengths. So this was a very tricky problem to separate what's really distant in high redshift and what is part of the galaxy. But we ended up with, you can see on the order of almost 800 young stellar objects with Herschel. All right, so this is kind of a little bit of the end of my story. So I've stepped you through that whole life cycle now. But then what is the ledger? What's the ledger book? So at the beginning I said, okay, how much dust is in the ISM? And so in this column here, it's always the LMC. This is always the SMC. I'm going to focus on the LMC numbers. I'm going to quote those. And remember, the SMC you'll see is about a factor of 10 lower. So the dust mass, 7.3 times 10 to the 5 solar masses of dust. How much dust is being returned from these stellar winds, from AGB stars, red supergiants, LBV masses. If you sum all that up, you have 2.5 times 10 to the minus 5 solar masses per year. And then here you have supernova dust production. This is based on the 87A result, 2 times 10 to the minus 3 solar masses per year. And then you have dust destruction by supernovae, 2 times 10 to the minus 2 solar masses per year. So you can see the destruction seems to be bigger. Star formation rate, 0.1 times 10, 0.1 solar masses per year. Stellar astration of dust, so that's sort of multiplying this times the dust to gas ratio. So this is how much dust disappears because we're just forming stars. 2 times 10 to the minus 4 solar masses per year. So what we have here is a net loss of dust at 1.8 times 10 to the minus 2 solar masses per year. So that's kind of a high rate of dust. Now, you'll note that I don't have a calculation for the dust growth in the ISM because we don't have ways to measure that yet. We know something's happening, but we don't know what the rate. But because this number is negative, I still ask this question of why does this galaxy have dust? And before I take your questions, I just want to point out that doing this type of work, I mean, the amount of discoveries we made in these programs is tremendous, and it's been really rewarding, but it is not possible without a large team of people because all these calculations and work requires many hands. So anyway, I thank them, and I thank you for listening to me. Yeah? Right. In terms of interaction, physical dynamical interaction, not as intensely as the LMC and the SMC do with each other. And this type of study of dust evolution has not been done in the Andromeda Galaxy, although I'm thinking about it with James Webb, when James Webb flies.
But the two satellite galaxies of Andromeda are mostly ellipticals. Do they have significant dust? At least the close-in ones are two ellipticals, dwarf ellipticals, aren't they?
Yeah. I don't know. My postdoc Libby is actually going to try to measure the dust production for M32.
Okay.
Just to see what's being produced. But there is not a lot of gas and dust. There's not a lot of interstellar medium. So it's hard to measure what's in the interstellar medium in the clouds.
In the case of supernova 1987A, you talked about dust being destroyed, and I was wondering why we're able to see it in that case of supernova.
Oh, right.
Okay. We need to repeat the question for the...
Oh, right, for the... Okay, so the question was, you mentioned that supernovae destroy dust, but in 1987A you see dust, so why do you see it in that case? And so the difference, or maybe I didn't make very clear, is that the supernova 1987A, the ejecta from the star, I mean, the explosion has created dust, that much dust. And it is, but it's the shock wave of the supernova remnant going out that is destroying the dust outside of that. So it's destroying the dust in the interstellar medium. So that's why we saw it. Also, it's very young. Supernova 87A is experiencing what they call a reverse shock, where the shock's going to come back. And so a lot of people say, okay, well, it's a half solar mass of dust, but all of it's going to go away with the reverse shock. Well, that's something we'll be able to explore, actually, over the next decade. How much does get destroyed?
So you're expecting the reverse shock to hit in the next decade?
That's what someone was telling me, yeah.
I just find 87A so fun.
It
because
is,
we
yeah.
get to watch things happen in real time that
You
we've
do.
never been able to see before.
So with James Webb, I'm going to use some of my guaranteed time to actually try to get a spectrum of that dust to figure out what is it made of, because it is limiting our models. So,
cool.
yes.
When you say that dust is destroyed, what does that mean?
It means that, well, dust is it's sort of all these metals that are solid, in a solid form. So when you mean destroyed, it means it's shattered all into the atoms. So that's why these depletion measurements, we're just looking at how much atoms of iron is there in the gas and how much should there be. And that's the fact that whatever's missing, sort of the missing.
So we had a
elements.
question from online.
Yes.
They wanted to know, are dust grains positively or negatively charged, or are they mostly neutral?
Oh, that's a very good question, very sophisticated. They are neutral inside the dense clouds, but near the surfaces where they're shined by light, they tend to be positively charged.
Okay. Questions from the room?
The dust-gas ratio, what was your definition again of the gas in addition to hydrogen?
Right, so hydrogen's the bulk of it, but then it's like, I think, helium, there's some fraction of it that's helium that we correct for.
Anything in addition to that?
No, I mean, basically, if you can account for all the hydrogen atoms and then correct for the helium, you pretty much know how much gas is there. I mean, we use all sorts of gas tracers to help us, like for the cold molecular gas, for H2, we can't really trace that very well with with the transitions, because it's a diatomic molecule. So we tend to use carbon monoxide, or CO, because it's asymmetric. We can trace its rotational lines at a low temperature and be able to use it as a tracer for where the molecular hydrogen is. That's part of the uncertainty in that gas to dust ratio map that I showed you. Is it's very difficult to map where the hydrogen is.
Okay, so we had another question from online wanting to know about the dust clouds themselves. What's like the average density in these dust clouds? I guess they'd probably want to know the temperature too.
Okay, the temperature in the clouds in the Large Dimensional Cloud are around 25 Kelvin, 22 Kelvin. So, I mean, really cold, but it's colder than 3 Kelvin, which is the cosmic microwave background.
But that's still minus 250 or so.
Yes,
centigrade.
you wouldn't want to
centigrade,
hang out
okay,
there.
which is around minus 500 Fahrenheit,
Yes.
right? Okay.
Yeah, you wouldn't bet.
Want to
on
put those
either.
in context.
It's not vacation land. It's not like being at the beach or something, playing in the sand grains. I mean, actually, sand grains is sort of an analogy to all the silicate grains and stuff. But the densities, it's very low. Gosh, I mean, some of the dust clouds, and I'm going to trace this in terms of the hydrogen content, right? Could be like, there might be 100 per cubic centimeter.
Right, that's...
I mean, it's rarefied. It's more rarefied than any vacuum that we can create on Earth. It's just very rarefied. And the reason we can see it is that we see large columns of it, and you map it, because there's just lots. The cloud's big, it's massive, but it's very diffuse.
Right, so it's like colder than anything on Earth,
Yes.
and more rarefied than anything on Earth, but yet we
Absolutely.
call it these giant dust clouds.
Yes.
Yes.
Yeah. Yeah.
Does the dust build anything? In other words, does it do something that creates?
It does. I mean, our Earth is made of dust grains. These dust grains have been floating around, but it creates things only when it gets gathered up, right? It creates a lot of hassle for all my optical astronomy buddies in this building, because they're like, oh, that dust, I've got to correct for it, because it's reddening my observations and it's making it dimmer. So it causes a nuisance that way. But in terms of creating things, when a star's formed, I showed you that disk and planets form around it, and the planets are really formed from the dust. The dust condenses nicely at the center, settles better than the gas. And that's actually a different mystery that someone else can talk to you about. But how do you get these grains to build up to create planets? They actually haven't figured that out yet, because it's hard to go from, okay, you can coagulate and they're bigger and bigger, but at that certain point, they can't figure out how they stick well enough together to build something bigger. That's a difficulty for them.
Peter?
I was wondering, would you consider dust to be destroyed by accretion, or is that considered destroying the dust? Because
No, no.
once the dust is accretes, I guess.
You mean
it's
to a
no longer dust.
You mean to a planet?
Yeah,
Is that what you
yeah,
mean? No, I wouldn't call that destruction. To me, right, I would say that's accreting into a really large dust grain.
We live on a giant dust grain.
A dust grain, right. No, because it's still a solid phase. So. Mhm.
Are there any, I guess, near-Earth dust clouds? Maybe not obviously near Earth, but maybe near the solar system?
Yeah.
That might swing through in the next 100 years or so, or close enough for us to observe directly?
They won't. Right. Okay, so I'll have two answers. One is that, I mean, we certainly observe dust and gas clouds in our solar neighborhood that, you know, people have observed. In fact, this whole depletion stuff I talked about, all of that has been done very local to the sun, because it's difficult to go beyond that. I think in terms of our solar system sweeping through next 100 years, well, I don't know. I mean, we might be passing through something now. I did hear a paper where someone used the Voyager spacecraft data to understand interstellar dust grains that were coming into the solar system. So it's quite possible that, you know, we are getting bombarded, but it's difficult. It was a fascinating paper, because somehow they were able to know it was clouds coming out. The Oort cloud, with the Kuiper Belt objects and stuff like that. I mean, but that's part of the solar system. I mean, so that, I think he was asking like a different interstellar cloud,
Yeah,
a diffuse cloud.
Everything within our sun's gravitational pull is kind of a unit. It travels
Right.
through space together, right? If that unit, however big you want to call it, swung through a massive dust cloud, I don't know, would it be easier for us to understand all of this?
It would be. I mean, actually, there's a group at University of Washington in St. Louis that is internationally famous. They have a meteorite lab in which they take meteorites and they smash them out to little parts, and they try to identify which dust grains are what they call pre-solar grains. And so they've actually have found and analyzed dust grains that were formed in an AGB star wind. And they're able to identify it because the isotopic ratio of like a carbon star has a very unique signature. When you dredge up the carbon-12 to carbon-13 ratio is very different than, you know, what we find normally in the universe. And so they're able to identify that and actually study those grains. And so that's probably the closest that I know where you come to try to study something that was created outside and actually somehow survived all the processing I've talked about. I mean, I think people were floored when they heard, well, what do you mean you found something that pre-existed the solar system and wasn't smashed to smithereens and rebuilt?
Okay, and let me just set time scale. The sun moves around the center of our galaxy in about 200 to 220 million years. So 100 years is nothing to the sun's motion through the galaxy. So I'm sure that in our travels we've made about 18 orbits around the center of the galaxy. We have passed through dust clouds, right? But it's not something that 100 years is going to make a lot of difference to our position in the galaxy. Okay. Other questions?
It's correct to assume that different sizes of supernova have different degrees of explosive force
Mm-hmm.
that can, as far as not destroy dust. If their forces are lower, does it not destroy the dust, just change the composition? And is there an correlation
Okay, you got to summarize that for the online because it's hard
Okay.
enough to hear at the front of the
Right. So what I hear, and please correct me if I'm wrong, you're asking that you imagine different stars, different masses will have different explosive forces, and that's completely true. And how does it affect? Because there's this difference in the carbon and silicate destruction? Does that affect?
So the number would be the type of dust that results or the degree of modification based on the
Right. So the question was, do we have evidence of how the dust gets, right? Is there a correlation between this supernova explosion and the type of destruction that it does? All I can tell you is that not as much evidence as we would like. I mean, there are a couple of supernova remnants that have been studied in some detail to show that dust is destroyed. But a lot of what is modeled is very theoretical. And that's why there's this whole huge uncertainty. Like I've told you, this dust destruction. And so some people in the field say, well, okay, but this is really a calculation. This is really a theoretical calculation. That's not as known as well as we might like. And so some people dispute that this dust is destroyed this efficiently. Other people believe this is gospel. That's mainly the theorist. Then they say, and the theorists say, well, what this proves is that dust has to grow in the ISM at a rate to nullify that. So basically things are steady state, and hence we have dust in a galaxy. But I think, I would like to see more observational investigation to do. I mean, we could do what you just said. I mean, can we find a correlation between the massive explosion and how much dust is destroyed, and really find hard evidence for that? That would be really good. That would be a huge step forward, in my opinion, if we could do that. But we don't quite have that yet.
I always just like to know, how did you get started in astronomy or not? That's, to me, that's as interesting as this.
Let's see. Well, a couple things. It's a bit of a circuitous path for me. It was a bit random how I got here, in the sense that I was always interested in astronomy as a child. Like at age 13, I took a science course, and I have to say, middle school teachers, if any of you are out there, you have probably the most impact on a kid's career decision. But I took a class, and everything they talked to me about was like meteorology. Oh, I want to be a meteorologist. Or geologist. Oh, I want to be a geologist. And we ended with astronomy. And I was like, oh man, I've got to be an astronomer. And then I found, then I took physics, I think the following year, and I found, I was quite good at it. I was good at math and physics, less good at English. And then when I went to school, I went to University of Maryland, College Park, actually, undergrad. And I said, well, you can't get a job as an astronomer. So I went into electrical engineering. I have a degree in electrical engineering and mathematics. But a neighbor of mine who was an astronomer knew I was a bright student and said, hey, do you want to work with me over the summer? I was like, okay. And so I worked at Goddard in some internships. And that was really cool. That was fun and exciting. And then when I neared the end of undergrad, I had to do an engineering honors thesis. And again, a friend of mine who was an astronomy major told his professor, and he called me up and says, how would you like to do it in astronomy? I was like, okay, as long as it has to have some engineering. He said, how about radio astronomy? I was like, okay. So I did a radio astronomy project, and it was really cool. I thought, wow, well, I think I want to go on to grad school. This is pretty cool. Maybe I'll try it out for a year. And so I tried it out for a year in grad school and said, if I really don't like it, I'm just going to move over. But I really liked it, so I stuck with it. Yeah.
All right, this sounds like a wonderful finish point. I am sorry to tell you that clouds have come in, and Duncan sent me an email, and we are not going across the street to the observatory. However, I did go out during Margaret's talk and get you a picture for tonight. Pillar in the Carina Nebula, all sorts of information on the back, some over there, some here. Remember to check the website for whether or not the south or the north is closed next month. I'll send it out on the email. Thank you all for coming. We'll see you in September. Take care. So somebody asked, I didn't want to bother you with this, because it says, wonder if the higher than average traces of lithium in our sun points to one or more large planets having been devoured by sun, or could asteroids account for it? And I told them that it's not really your field.
No, I wouldn't know the answer.
That's what I thought, so I didn't want to bother you.
Yeah.